Hey hi and welcome back to the part 3 of Introduction to Capacitor. I hope that you enjoyed the previous video, okay? And I assure you, you will enjoy this video as well, okay? So let's start with this video now. So we were discussing the purpose of capacitor, okay? And we were on this point, which is filter. And I told you that we will discuss the impedance versus frequency plot in this video, okay? So let's discuss the impedance versus frequency plot now. So this is basically the impedance versus frequency plot for the capacitor of value 0.1 microfarad or 100 nanofarad, okay? And you can see here the impedance versus frequency plot is denoted by this color. So this is the impedance versus frequency plot, and the ESR of capacitor is actually denoted by this particular color. So you can see this is the ESR of capacitor at different frequency, okay? So on the x-axis there is a frequency, and on y-axis there is an impedance corresponding to that particular frequency, okay? And this particular plot is actually starting from 10 kilohertz and it's ending up and it's going up to 10 gigahertz, okay? Now here you will have a question how exactly this impedance versus frequency plot came, okay? So let's discuss that now. We discussed that the impedance is mainly contributed by the three components in case of capacitor. The first one is resistance, then the second one is inductive reactance, okay? And then the third one is capacitive reactance. And we discussed that the impedance is actually mainly contributed by the capacitive reactance, okay? So this particular value is actually dominant in case of the impedance of capacitor, because the value of this resistance and inductive reactance in case of capacitor, it's actually less. That's why this impedance is mainly contributed by the capacitive reactance, okay? And you know, capacitive reactance is actually given by Xc is equal to 1 by omega c, okay? And we can write omega as 2 pi f, okay? So if I substitute this 2 pi f here, then we can write this as 1 by 2 pi fc. Now, in order to calculate the capacitive reactance for a specific frequency, what you have to do, you have to substitute that frequency here, and we know the capacitor value, it's going to be 100 nanofarad, okay? So let's try to calculate the capacitive reactance at this particular frequency. So I will substitute this particular value here. So it's going to be 1 by 2 pi, 2 pi into 10 to the power 6. So that's going to be 10 into 10 to the power 6. So that's going to be 10 to the power 7 into the value of capacitor, which is 0.1 microfarad. So this entire entity, it's going to be 1. So it's going to be 1 by 2 pi, okay? And this gives us Xc is equal to 0.159 ohms, okay? So that's basically the capacitive reactance for this particular frequency, which is 10 megahertz, okay? So if you see the value for the impedance at this particular frequency, then you will find that the impedance value is actually near to this value. So X is equal to 0.159 ohms. So you can see the impedance value at this particular frequency is around 159 or somewhere around that 159 milliohms, okay? And as we discussed, the impedance is mainly contributed by the capacitive reactance, and the effect of rest of the two components is going to be the less, okay? So that's the reason, just by doing the calculation for the capacitive reactance, we got this particular value, which is actually close to the impedance value, okay? And if you calculate the capacitive reactance for this particular frequency, which is 1 megahertz, then you're going to get around Xc is equal to, you know, 1.59 ohms, okay? So you can see 1.59, so it's somewhere around that, okay? 1.59 ohms, okay? In the same way, for 100 kilohertz, you are going to get 15.9 ohms, okay? So this is actually 10 ohms, so here it will be 20 ohms, so somewhere it will be 15.9 ohms, okay? In the same way, this is 1 ohm, so it's going to be 2 ohms. So we calculated capacitive reactance as 1.59 ohms, so it's going to be somewhere around here, okay? So this is how basically the impedance versus frequency plot in case of capacitor is calculated. Okay, so you just have to substitute all these frequency in this particular formula and you are going to get this impedance versus frequency plot. Okay, now how exactly this impedance versus frequency plot is going to help us, you already know that. Okay, we discussed that the frequencies for which the capacitor provides low impedance, all those frequencies will be actually bypassed by the capacitor towards the ground, right? So you can see here, this is actually 100 milliohm. So let's consider all the frequencies below 100 milliohm. Okay, so to all these frequencies starting from let's say 10 megahertz till 20 megahertz. So this range of frequencies, all these frequencies are actually going to face impedance of 100 milliohms. So this is actually almost a short circuit. So for example, let's say that this is a power line and this one is ground line, and between that the capacitor is connected like this. And if there is a frequency of let's say 10 megahertz here, okay, then that particular frequency is actually going to see this capacitor as a complete short circuit. So this 10 megahertz frequency will actually travel through this capacitor towards the ground, and that particular frequency will actually not available here on the output side. So if you connect this point with respect to this point on the DSO, then you will see that you will get nothing here, okay, on the output side, because this frequency will be completely eliminated by the capacitor, okay, by showing a low impedance path. Okay, so all the frequencies which are actually belonging between 10 megahertz to 20 megahertz, all those frequencies will be actually bypassed by a capacitor with a value of 0.1 microfarad. Now this does not mean that these frequencies, for example 1 megahertz, this particular frequency will not be bypassed by this capacitor completely. This frequency also it will be bypassed, but for this frequency if you see the impedance provided by this particular capacitor, it's actually 2 ohms. Okay, so I will just extrapolate these points. So for this particular frequency you can see 1 megahertz, the impedance is 2 ohms. Okay, so this capacitor is actually going to behave like a 2 ohms impedance. Okay, so most of the signal it will go like this towards the ground, but some signal you will see that it's going to appear on the output side. Okay, so generally for these frequencies where the impedance is like 100 milliohms or below that, those frequencies will be completely eliminated by that particular capacitor. Okay, because here in this range the capacitor is actually providing very low impedance. Okay, and if you see here for 10 kilohertz frequency, the impedance provided by the capacitor is 200 ohms. Okay, so this capacitor is going to behave like a 200 ohms impedance. If you provide a signal of 10 kilohertz on the input side of capacitor, then that particular frequency it will not travel towards the ground. Okay, you will see that frequency on the output side completely. Okay, if it is sine wave of 10 kilohertz on the input side, then you will see the same sine wave on the output side without any kind of attenuation. Okay, so let's consider that you provided a signal of a 5 volt DC on the input side, and along with that signal there is a noise of 10 kilohertz. Then you are going to get the 5 volt signal on the output side. Along with that you will also get the 10 kilohertz signal on the output side. So that 10 kilohertz noise will not be bypassed by this particular capacitor, because that 10 kilohertz noise is actually going to see this capacitor as a 200 ohms load. Okay, and if you provide a 5 volt signal on the input side with a noise of 10 megahertz, then that particular signal with 5 volt DC and 10 megahertz noise, that 10 megahertz noise will be bypassed by this particular capacitor, and you're just going to get a 5 volt DC on the output side. So the AC component which was present with 5 volt DC signal, those AC components will be bypassed by this particular capacitor, and on the output side you're just going to get a pure 5 volt DC. Okay, so I hope that this particular point is now clear. Now this is basically a impedance versus frequency plot for a 10 microfarad capacitor. Okay, And you can see in this plot, the low impedance, which is around 100 milliohms, it is available at this particular frequency, which is 100 kilohertz. So this is basically a logarithmic plot. So this is going to be 200 kilohertz. This one is 300 kilohertz. This one is 4, 5, 6, 700 kilohertz likewise. Okay. So 100 milliohms impedance is available at 200 kilohertz. Then 100 ohms impedance, it is also available at this frequency, which is 20 megahertz. Okay. So 20 megahertz. So if you use this particular capacitor, then you will be able to bypass the frequencies starting from 200 kilohertz till to 20 megahertz. Okay. So this capacitor is capable of filtering all the frequencies which belongs to 200 kilohertz and 20 megahertz range. Okay. So I hope that this particular point is now clear. Now let's consider that on the power line you connected two capacitors in parallel, and the value of one capacitor is 0.1 microfarad. Okay. And the value of another capacitor, let's consider that it is 10 microfarad. Now let's see how exactly the impedance versus frequency plot for these two capacitors which are connected in parallel will look like. So this is how basically the impedance versus frequency plot for a 0.1 microfarad capacitor and 10 microfarad capacitor on the same plot, this is how basically it's going to look like. Okay. So this is the curve for the 0.1 microfarad capacitor, and this is the curve for the 10 microfarad capacitor. So 10 microfarad capacitor is good at filtering the frequencies starting from this point till this point. Okay. So till this point, and 0.1 microfarad capacitor is good at filtering the frequencies starting from this point. Okay. And till this point. Okay. Till till this point, which is 10, 20, 30 and 40. Okay. We considered, so this one is actually going to be 200 or 150 milliohms. Okay. So let's consider 40 megahertz also. Okay. So let's consider 40 megahertz as well. So starting from 200 kilohertz till 40 megahertz. So this range of frequencies you will be able to filter out when you connect two capacitors in parallel. Okay. So I will show you the equivalent impedance versus frequency plot for these two capacitors now. So you can see this is how basically this black line that you see that actually represents the impedance versus frequency plot for 10 microfarad capacitor and 0.1 microfarad capacitor in parallel. Okay. So you can see here the combined plot becomes for 10.1 microfarad capacitor. When you connect two capacitors in parallel, it will actually get added. So this is how basically the plot look like. Here you are actually getting a peak. So, and for this particular peak, the impedance is 200 milliohms. So it's completely fine. Even if there is a peak, no problem. 200 milliohm impedance is also very less. So a good range of frequencies you are actually able to filter out when you connect multiple capacitors in parallel. Okay. So remember this particular point. So I hope that now you are crystal clear with how exactly the capacitor filter out the frequencies. Okay. So whenever you will have to bypass unwanted frequency, now you know how exactly or what capacitor you have to use. Okay. Alright, so that's what I wanted to discuss in this video. I hope that every single thing that we discussed is now crystal clear to you. And if you still have any kind of doubt in this video, then definitely you can ask me, because this part that we discussed is actually very important from circuit design point of view. Okay, no matter what kind of circuit you will design in your professional life, this knowledge that you get in this particular video is actually very important. Okay, and you will realize this when you will work or when you will start working on the products, or when you will start working on your project. Okay. Alright, so that's what I wanted to tell in this video. I hope that you enjoyed this video. Now I will see you in next video, which is Introduction to Capacitor Part 4.